All right, well, I am really honored to be here. I have gone to many of events that Jean-Luc organizes, and they are always very good. And as he said, we know each other for quite a few years, so it's always a pleasure to get an invitation from you. So today I'm going to be talking about, as I say, building electronics from solution. I always liked to work on applications for materials, and from my undergraduate, I started working on solution process semiconductors. Hence the building electronics from solution. I thought I would just tell you about my move. I didn't move very far. I was working here at the Palo Alto Research Center, and I moved to Berkeley on the other side of the San Francisco Bay. And the reason I moved there was because the department had a vision, has a vision to start a lab that's right now it's called the Post-Silicon Lab. I'm sure it's going to change names. This lab is really dedicated to flexible electronics. And the idea is that we will work with whichever material that you can deposit in whichever substrate to achieve flexible devices and flexible systems. So that's why we say here all on all or X on Y electronics, because the idea is if we have to mix and match nanowires with organic semiconductors, with inorganic semiconductors that are processed somehow so that they are compatible with flexible substrates, we would do it. The idea was to have really look at different applications that could be very simple applications like disposable electronics, where you have some sensors that are integrated with the packaging. And now you can imagine that since you are printing things in the packaging anyway, why don't you print something that is functional that will give you some indication of how good, how old, how fresh the product is. Or paper like displays, which is an application that it's much more developed today than many others. Or just electronics in general, or PV, and with the idea of really having new manufacturing technique. So I would like to really impress you and give a talk here with the things that I have done at Berkeley. Since I arrived in Berkeley, once I conquered my space and I took away everything that was there, it was April of this year, and this is how my lab looked like. This is what I have done there. My student sent me a picture yesterday while I was in the airplane of how the lab looks like today. So you can see that, first of all, I have students. And then there's equipment, and they were moving in because they finally finished the facilities work. So that's what I have accomplished there so far. Here are the brave ones, the first ones that joined my group, since I am new and they didn't know how I was, what my style was. So I have two undergraduate students that were taking my class, and then they came and approached me and asked to join my research group. So I guess that's a good sign of the teaching. And 5 PhD students. This is what I've done so far in the 6 months that I've been at Berkeley. So today, what I'm going to talk to you is really related to the research that I did with my group at PARC, at the Palo Alto Research Center. And the outline goes, I'll talk a little bit about the motivation for flexible electronics and potential applications. And I will spend a lot of my talk talking about materials and processing techniques and what is involved when you are really processing materials completely from solution, where all the very well established patterning techniques are not used. Thin film transistors, because thin film transistors are really the heart of electronics. So for printed electronics, we need to understand and characterize thin film transistors very well. And finally, I will finish with the development of this application that's called the blast dosimeter, and I will explain a little bit more. It's really how it says. It's a dosimeter for blasts at the end, which was a system that we developed at PARC and brought together many components, and I'll spend time there. So every time I talk to students, I like to say a few words about PARC, because PARC is a special place where it's, you do industrial research, but you're still doing research. So at PARC, the product of that company is research. So for students that is trying to figure out what to do after your PhD or even during your PhD, there are internships that are available at PARC. And it's really a great way of getting a different flavor of research, where it's more applied. You have to work on problems that are real problems that different industries have. So at PARC, there are 4 divisions, 2 computer science, 2 computer-related labs, and 2 hardware-related labs. I worked on this one, the electronic materials and devices, where there was, you can see here, there was a range of projects or areas of projects, going from large area electronics, clean tech, and also some biomedical systems. So PARC exists for 40 years. It was funded by Xerox to really be the lab where the new technology, or the technology that's going to be used in Xerox products in 20 to 30 years from now, was going to be invented. And there were lots of things that we use today that were invented at PARC. For example, the laser printer was invented at PARC, and Xerox says that with the profits that they got from that research, they justified the existence of PARC for more than these 40 years. Adobe, for example, is a technology that Xerox did not commercialize, but the researchers who had that IP left the company and started Adobe. And you know, the list is quite long, so it's a wonderful place to work. I spent 8 years there because it was so good. So the business, as I said, for PARC is really you do research with companies that are clients, and also government contracts. I'll show you an example of a government contract. Actually, I could only talk about the government contracts. And there are partnerships with startup companies, new companies that are created from PARC. And also, of course, a lot of licensing and technology. There's a lot of IP that PARC licenses for lasers, and also for large area based on amorphous silicon that was done, you know, the initial work was done there. So I encourage students to look at the web page and look for the internships. It's really great. So going to the topic of this talk is really flexible electronics, or more printed electronics. The list of the motivation why one would want to work in a printed and flexible electronics is quite long. You start off with the new materials. So if you want to print materials, that means that you cannot work with silicon wafers anymore. You're not going to work with polycrystalline silicon or amorphous silicon. You're really going to work with completely new materials. So if these materials are completely new, the interfaces that you have in your devices are also very new interfaces and not so well studied. The problems that you have, the scientific problems, are really challenging and unique. So for the scientific perspective, this comes from the novelty of the materials. Now, if you are processing these materials in a different way, you're really creating a new fabrication technology which allows you to think about how you are going to integrate different components. So if we've established technologies, if you want in one area a laser, an integrated circuit, a MEMS type of sensor, you have to rely on really different types of fabrication techniques. if you are processing everything from solution and printing especially, you can start thinking about how to mix and match these materials so that in the same substrate you can print a photodiode, an LED, and some circuits or a display. For the industrial people that are interested, there is a much lower capital investment, and that means that when you want to start a new fabrication, a new fab, you always need to invest in area, the footprint of the fabrication facility, but also in equipment. And here, in printing, the idea is that you're really going to deposit materials only when you need the functionality of that material. It's really like printing a document. You don't print ink everywhere and then remove ink from the places where you don't want the black, and then you only print the black where you need the black. So the idea here is the same. You only print semiconductor where you need semiconductor. So there's no etching, there's no subtraction, and there's no waste of materials. And with every process that you have in conventional fabrication processes, you have an equipment and a cleaning equipment and a robot to carry things around. So it turns, there's a promise that it will be much lower capital investment. And then it goes on with, it will be more compatible with large areas, because if you can really do everything by printing, you could cover really large areas and make it in substrates that are very lightweight, because if you have a large area, you want that to be lightweight too. Otherwise, how are you going to hang things, transport things? And really the goal of this area started off by saying, okay, let's make this type of screens that is really what we have here on the desk, not really just a projection screen. Make everything active so that you have really large pixels and everything is flexible, and once you are not using it, you just roll it up and put it away. So you can keep going. One of the important things here is that a customization, if you're using printing, is very easy. Like you can print 500 pages out of your printer, and all those 500 pages are different from each other. And you could possibly do that with printing technologies too, especially if you're using digital deposition, meaning that you don't have a master that will be printing the features that you need. So there are several excuses to work in this area. And depending if you're in industry or academic, you are going to say that this is one of the reasons you are working here. I believe in many of them. I really think that many of them are true and valid. So why don't we go to a shop and buy something that's flexible? There has been flexible electronics. There has been demonstrations of flexible displays. And displays were really the first motivation. People wanted to work on displays just because the market is so big. So there were demonstrations of displays, but what was really achieved on displays was that people were able to make the display media flexible, and the backplane of the display media, what's driving the display, flexible. But all the drivers, all the power supply, everything else in the display is done with conventional electronics, with rigid electronics. So that's why all the demonstrations that you see in this case are either bistable media, where you write the image, you disconnect from the black boxes, and then you hold your flexible display and say, look, it's flexible. It's valid. I mean, at PARC we did that too, because it was still hard enough to get the backplanes to be high yield and flexible and work well with this display media. But all the applications you can see in this one has something rigid associated with it. So the bottleneck in this technology is really the driver electronics and the power. There are other applications for flexible electronics or for printed electronics that people work on. Some of them are very simple, like in this battery tester. You can screen print everything there, and then you just connect your battery, and it will change color. It's electrochemical change, and you see if the battery is good or not. Or you can make the battery itself flexible. And I'll show you later that even that technology, there are some limitations. Of course, solar cells, everybody's very interested in solar cells because you would like to cover large areas with solar cells to make power. There are other problems associated with solar cells, but it's definitely a valid application. And again, other types of displays or even keyboards or touch things that you want to be flexible, not only to be able to fold it, but to make sure it doesn't break. So the goal of printing, as I said at the beginning, is really to go from photolithography, where you have several steps before you get the feature that you want on your substrate, to something that you have only one step for depositing and patterning the same feature. So you can see the advantage here, and this is really the holy grail of this technology. But it's not so easy to achieve that, and I will just go through certain points where you have to have control over the deposition here. The first thing that you do if you work on printed electronics is that you learn how to measure contact angle. And you spend a lot of time worried about this equation here, which basically tells you the interaction between a solid and a liquid will depend on the surface energy of the solid, the surface tension of the liquid, and the contact angle. That means you really have to control, if you take a liquid and you put here on the solid, is that going to spread a lot? Is that going to de-wet? What's going to happen to your feature? And you can see here just a simple example. If you take the same print head, same equipment for deposition, the same ink, you just change the substrate surface energy or the contact angle. You see that if you go from a very low contact angle to a high contact angle, your feature changes from a very wetting condition where the ink likes the substrate and really wets the substrate, to a condition where the ink is de-wetting from the substrate. And that goes with the feature will change here in this case from 350 microns to 100 microns. So there is a huge difference in the feature sizes that you get, which is something important for patterning devices. But there's also an implication on adhesion of this material to the surface that you're using. Obviously, if the substrate is, if the solution really wets the substrate, that means it will have good adhesion. But if it's de-wetting, it doesn't really have good adhesion. So if you fix those parameters, you can get features that look like something that you could use in electronics, even though in a much different scale than what you do when you're using photolithography. The other problem that's very well known when you're working on printed electronics is the so-called coffee stain effect. And the coffee stain effect basically has to do with the fact that it really comes from, the name comes from the rings that you get if you have a coffee spelled in your, or if you put a coffee mug in your desk and you spill coffee, you get like a ring of coffee. So here is the same thing. When you deposit a drop in the substrate, you may achieve a condition where the drop is pinned to the substrate. And if the drop is pinned to the substrate, it means that as the solvent evaporates, the drop can't really shrink. So the drop is there, it's really pinned to the substrate. So because of that, then you get a different evaporation rate in the edge of the drop than you have in the middle of the drop. And that change in evaporation rate, or that difference in the gradient in evaporation rate, creates a flow that brings all the material that you had in your solution towards the edge. In certain occasions, you can get a perfect ring with no material deposit in the middle. And that's really something that we don't want here. And I'm sure there are applications that you can look for with this case of coffee stain effect, but here is really not what you want. So if you look at the profile of this feature, it's terrible. And here there is another problem that comes up from coffee stain effect, which is that the edges of your feature become so thick that you get to something that looks like mud. When mud dries, you get all these cracks here at the edge. That's exactly what will happen to a feature if you don't control now the surface tension of your liquid, of your ink. So there are things that you can do. Well, one thing that you can do is to change the surface energy of the substrate so that pinning doesn't happen and the drop can freely shrink as it's evaporating. Or, and that's in some cases is not really desired, because that means that the solution is basically de-wetting from the substrate. Or you change the surface tension of your ink or of your material, of the solution, in order to compensate for this coffee stain effect. So there is another phenomenon that's called the Marangoni effect. And the Marangoni effect basically is a flow that happens opposite to the coffee stain, and it brings things from the edge of the drop towards the center of the drop. And in order to achieve that, what you have to, the condition you have to have is now a gradient on the surface tension of the liquid. So if you mix solvents that evaporate in different rates, at the edge, where the evaporation rate is higher, the solvent that evaporates faster will leave the drop, and at the edge, the drop will have a very high concentration of the solvents that has the lower evaporation rate, while in the middle, you have a mixture. So because of that surface tension gradient that you create on that drop, a different flow is formed, and then you bring the material to the middle of the drop. So you go just by manipulating the surface tension, and I shouldn't say just by manipulating and understanding the surface tension of the liquid, you can go from this type of features to something that is like more like that, where it's much more acceptable for electronics. So let's build a device from solution and think about all the things you have to really understand and have under control. The example I have here is a top gate thin film transistor. So thin film transistor, you have three electrodes, two that are called source and drain, where you have the current going here in the channel of the TFT, and one that's called the gate that you modulate that current. Between here on top of the source and drain, you deposit the semiconductor, and you have the gate dielectric and then the gate electrode. So let's say you want to do a printed device, and you go and you buy materials. You can go to the Aldrich catalog and get all these materials that I have here. You buy these materials and you try to make a device. I bet you it will not work because you really have to have all these things under control. So look at the substrate first. You start with glass substrate. You're not going to try to make something flexible first time. The contact angle of the glass is about 10 degrees. And then there are two silvers here that I am giving as an example. Once you figure out how to print the silver and you measure their contact angle, the water contact angle, one is around 50 degrees, one is around 100 degrees. So if you made a TFT like this, when you come to print the semiconductor is going to see 10 degrees here at this interface and 50 or 100 degrees at the contact. So obviously the semiconductor will only wet the channel and will de-wet from the electrodes. So that's not going to be a very good device. So what you have to do is change the surface energy of both of the substrate and the contacts, so that when the semiconductor is deposited, apart from not dissolving the materials that are already there, you will not see a difference in surface energy. So working on materials that can both modify the surface energy of the substrate, modify the surface of the electrodes, and add some electronic properties so that injection or transport becomes better in that interface between the metal and the organic semiconductor is very important. So here, that's what we did. We used this material here to modify the silver, and this material also makes kind of locally dopes the contact there with the semiconductor. Then you go on building your device. Best dielectric materials deposited from solution are very hydrophobic materials. Basically, Teflon is an excellent gate dielectric. Cytop is an excellent gate dielectric, but they are very hydrophobic. So again, if I want to print the silver on top of that material, I'll just get like isolated drops that are de-wetted, and I'll not get this nice line that I need as a gate. So you change one material, you have to characterize everything again. You change the substrate, you characterize everything again. And that's how printed electronics works. It's very easy. So let's look at the materials, the device. What happened? So if I just bought the materials from the catalog, followed the steps, and made the devices without controlling surface energy, these are the type of results that you would get. In a TFT, the thin-film transistor is really a switch. So when it's off, you want very, very low current. When it's on, you want very, very high current, and you want it to go from low current to high current as fast as possible, which is this threshold here. It's this slope here, which is called the subthreshold slope. So you want this to be almost perpendicular and as high as possible and as low as possible. You see that these two TFTs are very bad TFTs. They have very high off currents, and they don't turn on very sharply. You can see here the mobility is very low for that case, for these two cases here. So if you're a chemist and you spend a lot of time preparing your super semiconductor, and you give to somebody who makes a device and tells you the mobility of your device, the mobility of your material is very low, I tell you, that may not be true, because what a device tells you is how good the device is, not how good the material is. So here is a very good material, but the device was a bad device. So once we fix the contacts and we fix the substrate, here's what we get. This is TIPS pentasene, and we get mobility around 1, and the mobility is independent of the metal that we are depositing. And you really get really nice characteristics. So the same material that we would report to our friends chemists that were bad is actually very good if the device is good. So keep that in mind when you look at results from devices. Now, if I'm printing, it's one thing to get one device to work very nicely, but in order for you to have technology and electronics, you really have to be able to make more than one device work the same way. So the example I use to show how reliability and uniformity is important when you use printing technologies is the case of a ring oscillator. Ring oscillator, one would agree, it's a very simple, basic building block for electronics. It has 5 inverters and only 10 TFTs. So only 10 transistors. If all your transistors don't work exactly the same way, or within a very, very small margin of error, the oscillator is not going to work. It's not going to behave as a ring oscillator. And what are the things that you have to control here? So here is the inversion, the inverter equation. And basically, there are only 4 things that you have to worry about: threshold voltage and mobility, and W over L, width over the length of the TFT. These two will come from the choice of materials and how you process your device. And these two parameters is you control with how good your printing technique is. So if you have these four under control, you will get really nice working digital circuits from printed electronics. If you have threshold voltage shift by stress, it's not going to work. If you have bad printing, where one channel is 20 microns, the other is 25, the other is 30, once you put it in a ring oscillator, the ring oscillator doesn't work. You can still publish a paper on how good one of the TFTs were, but when you look at the technology, it's not a viable technology. So it's really important to look at reliability when you're developing something new. So I did my PhD in polymer blends, and I really believe that if you are working with new materials, you really should take advantage of what the material has to offer. And in many cases, we try to make organic semiconductors behave exactly like inorganic semiconductors. And we shouldn't, because they are different. So one of the things that I did here was one of the problems I had when I was trying to make backplanes for displays was the stability. So my backplane was based on a bottom gate TFT, which means now the gate electrode is at the substrate, and then I have a dielectric and the source and drain. The last thing I was depositing was the semiconductor. These organic semiconductors are not really stable in air, but they are also very fragile, so it was difficult to deposit something that would encapsulate those devices so that they could become more stable. So here, one thing that I did at PARC was to use polymer blends, where I mix the semiconductor with PMMA, which is an insulator, and then I manipulate the surface tension or the surface energy of the substrate, the gate dielectric in this case, so that there would be preferential wetting of the semiconductor at that interface where I wanted to form the channel. So then all the semiconductor, or a lot of the semiconductor, is deposited at that interface, and the top interface has PMMA, which is the insulating material. So you essentially achieve this self-organized double layer, where the semiconductor is now really protected by this insulating layer. There are no pinholes in this process. One of the very good things about phase separation. And you see that now I bought myself some window of processing where I could deposit another material at the top if I wanted, because the semiconductor is protected by the PMMA. So what happened then? You can see here that from a device that just in a few hours was moving over, the off current was not so good, the subthreshold slope was really suffering with a few hours exposed in air. You get something that is very stable in air for many hours, and it works even better than what you had when you only had one material there. What are advantages for technology? My blends here were composed of 20% semiconductor, 80% insulator. So my precious material, new material semiconductor, is really not used very much. It's only 20% of the blend. And if you look at how paint is done, paint is really composed of many elements that do their job. So I think in printed electronics, it really should be the same. We should look at materials that help the semiconductor or the new electronic materials do their job well. And this is just a simple example of that. So when you get everything to work, we were able to demonstrate fully printed TFT backplanes, where our process was only 4 layers. There was one layer to deposit the gate layer. The gate layer in the TFT backplane is really turning the pixels on and off, which is this green layer. The red layer is the data level where you send the information that you want to write in the display. And the blue dots are the printed semiconductor. So this was the file that I had in the computer. And then you say print, and this is the results that you get. So you can see here the resolution. These pixels are 340 microns. This pixel is 680 microns. Just to give you an idea, if you were to print a screen that this big, your pixel would be 1 to 1.5 millimeters square. So the resolution that you get for printing here is really good for large area displays. You don't need to go smaller. You need to go smaller when you for other applications. And here we took this backplanes, and we integrated that with e-ink, and we showed that even though the polymer, the semiconductor was a polymer and the dielectric was a polymer, there was no silicon here, not the substrates, not the dielectric. You can run the same media that you have in the e-book readers today. 4 years ago or so, people were saying, well, where is electronics really going? What are the applications? Where can we go with these materials? Because people start thinking, oh, you just get mobilities of 0.1, 0.2, there's not much that you can do. And today, we see that we have not only materials that have much higher mobilities. Mobilities around 1 is what you get for amorphous silicon, and you see how much is done with amorphous silicon. But also materials that are stable and can be printed. So I'm going to use just a few slides that I borrowed from my friend Hagen Klauk to show you other advantages and other development that happened in these 4 years for printed electronics. So we went from low mobility and having only a p-type channel with good stability, because back then, if you take, for example, the pentacene example, you have all your orbitals here, and you have the LUMO and the HOMO, which are the equivalent of the conduction band and valence band in conventional semiconductors. And you wanted to make a device with these materials. You could deposit very high work function electrodes as your electrodes, and metals that are very stable and have high work function that will align very well with the HOMO level. So when you have that situation, you can make a very good p-type device where it's easy for holes to go through this semiconductor. It's a very stable device because you're working with high work function metals. Now, if you had to do an n-type device, what you had to do was to change the work function of your metal, bring the work function down or up in this case energetically, so that you could get a transport of electrons. That's where the problem came, and the OLEDs battled with that for so many years because it has nothing to do with the semiconductor. It has to do with the fact that the metal is not stable, but in order to inject charges in that semiconductor, you need that metal. So chemists are amazing, and today what they do, they actually change the energy level of the semiconductor so that you can now align the LUMO level with very stable metals. And that's how we start seeing N-type devices that are very stable because the metals now changed. And there are other things that people can do with chemistry that will change this energy level so that you have a very stable response for P and N-type materials. So this opened up so many more opportunities in printed electronics, because now we are not only working with PMOS, we can start thinking of CMOS, complementary electronics. So here I worked closely with two companies, one based in the UK, one based in Chicago, where one was providing me the P-type semiconductor, the other one the N-type, and my group worked on getting a process that works for both, for P and N-type. And the idea here, the goal, was not to get the most efficient or the highest mobility, but to get a process that was feasible for both materials. So use the same contacts, the same gate dielectric. And you can see here that we got very good results. For the P-type, we got mobilities of 1.6. The N-type, we got mobility of 0.8. And that was really good advance progress in this area, because we went from a case where we had a TFT backplane. TFT backplane is very simple. You have one TFT that is your switch and one capacitor. You use only PMOS or NMOS, depending on the type of TFT that you want to use. Two things that can look much more like this now. If you have CMos, you have lower power consumption. You could possibly get lower operating voltage, and you could integrate sensors and memory to make more complicated systems. So here what I'm showing is like a system that has a lot of sensors. For a sensor to work as a sensor, you need an amplifier, or otherwise that sensor is a detector, not a sensor. You need an amplifier that will process the signal and send to some other electronics. In this case, well, it can be a trigger logic where you want to know when the electronics will turn on or off. Could be timing logic, when the event happens. And the memory is important, because the memory or the display is really the output of that system. So as I promised, we worked on a system like this that was very complex and involved several components, which was this sensor tape. This was funded by DARPA. And what they wanted was a tape that would measure the amount of explosions that soldiers are exposed to. The reason they needed that was to prevent brain injury. They knew that depending on the amount of explosions that you are exposed to, you may or may not have brain injury. And there is a certain threshold that if you can catch, people don't get hurt. But they didn't have a viable way of preventing that. And everybody that was coming back from the war, about 70% of them had brain injury. And that's something that the government's not very proud of. So they wanted to monitor that. And it was a medical device per se, because it was going to be part of the medical record for everybody that was there. So what did they want? They wanted the system to measure pressure, light, acoustic levels, and acceleration. They didn't want any wire coming out of it. No RF transmission of data. They wanted the system to last for 7 days and cost $1. So we proposed to do everything by printing. What encouraged us was in the specs. They said that all they needed was the memory to record 40 samples at 5 milliseconds intervals for 200 milliseconds total time. That means the electronics are very, very slow. So using conventional electronics here would be an overkill. So we thought, okay, 200 hertz, maybe printed electronics could do. And that's what we set ourselves to do. And we worked on this project for just over about 2 years. First thing we decided was if we were going to use complementary or unipolar electronics. Use P and N, or only N or only P. As I said, there are advantages of using complementary logic. One is the power consumption, but the other one is that if you use complementary logic, you had a much larger noise margin than you would get if you're using unipolar electronics. So since we had friends that could make materials and we're making P and N type, we decided, okay, we can have a shot on printing CMOS, which was something that was not done before. It has, I believe we were the only ones that did complete CMOS printing, truly printing. So Then you have to look at how these devices are working. I'm sorry if I'm having the electronics, but I'm sure you can understand this. So there are two types of circuits that we would make, analog circuits or digital circuits. In the analog circuit, you will set your input very near the inversion point here for the amplification. This is where it happens. So if your device that is now a P-type and an N-type TFT has threshold voltage, which means that threshold voltage shift. It means that the curve shifts as you apply more bias. Then this point here at the inversion point will be moving around as this device operates. So if you don't match the P and the N type very well, so that the threshold voltage shift, even though they occur in different directions, if they don't cancel each other, your analog circuits are not going to be very stable. Digital circuits is a different story. Digital circuits, you will set your input voltage to either a low or a high level, which are right here, either a high level or a low level. If this middle point is changing, but your high and low levels are constant, if the whole curve is shifting, that doesn't matter for digital circuits. So what we decided to do in our design was really to use CMos complementary in all digital circuits that we had in our device, in our system, and use PMOS in all the analog circuits that we had. Just based on the threshold voltage shift. We know that there is threshold voltage shift, so you have to design for it. So with that, we were able to demonstrate several building blocks for the electronics that we needed. The ring oscillator, a shift register. The shift register was really to write into the memory. An amplifier, you can see here the amplifier is doing its job. And that was all the electronics that we needed for that blast dosimeter. If you look at the TFT count or the system design, this is how it looked like. The black box here was all memory. You look here how many TFTs you needed per electronics, and the total number of TFTs is about 22,000 TFTs in each tape. So if you're printing, you have to have all these things under control. Most of the TFTs, as you can see, are coming from the memory. And I'll talk a little bit about the memory now. Memory. So the memory, we decided we didn't really have space for digital memory. So we went with an analog memory. And there were two things that we looked at before we decided how to go. We could look at just using the threshold voltage shift as memory, but we decided that that process was actually too slow. And we know that you can fix threshold voltage shift by shining light or applying an opposite voltage. So we didn't go too far with that. So our choice was to change the gate dielectric now in the TFT to a ferroelectric material, where you could change the polarization of that material and use that changing polarization as the memory. This was first demonstrated at Paul Blum's group, and we basically follow some of their steps, where you have a TFT now that it has this copolymer that you guys must have heard because Solvay makes them. That shows this dipole, and you can change this dipole depending on the voltage. So you can see the higher the voltage that you apply to that TFT, the higher the hysteresis. And that's how you could define the on and off for your memory. So how things look like. Now for our memory, in each memory pixel, we had one TFT that was working as a switch, just turning on and off to give us access to the memory, and the other that was a memory. So we had to integrate all these materials vertically. That was fun. And you can see here that in the switch, there is no hysteresis, while in the memory, you have hysteresis on purpose to be your memory. That's how it looked like. How did we measure it? How did it work? So basically, the select line here would be connected to a sensor, and the data line, it was connected to a shift register, and that's how we would access this pixel that we would need to open this switch to write into the memory. So when we were writing, everything, if we wanted to write into this memory, everything was grounded. Only this pixel, only this switch was open, and we could write here. This is very important because in this way, we don't have crosstalk. When I try to write into this memory, I am not actually writing into that other memory there or any other pixels that are below this, select line and this data line. When you want to read, you ground everything else, and you only access this through another metal line here. You only access that memory pixel that you had here. And this is how it looks like when you print, and that's how it looks like the whole memory array. This paper actually was just published in Organic Electronics. So how do we explain to the military, our customers, that the memory was working? So we worked on displays for so long. We just made a display out of the memory. We took the e-ink, and if you look at the schematics here, basically you have switch and you have a capacitor. So depending on how much charge you put in the memory TFT, you could switch e-ink at different levels of gray. And that's what demonstrates here, that depending on the voltage that we apply to each pixel in that array of memory, we would write different things. You can also see that the resolution of the memory was not very high. The pixels are quite big. So I'm running out of time, but I'll talk about sensors a little bit. Because when you look at sensors, you have so many options of different sensors that you can develop. And in this case, we went with piezoelectric sensors because for once, piezoelectric sensors are very good for power. They have low power consumption, and we wanted this tape to be in the helmet for 7 days, so we didn't want to have to put too many batteries. And also, it was good for transients. And this is really what we needed. There was an explosion. The sensors were always on. There was an explosion, there's a transient, there would be a peak and the response from this piezoelectric, and after the explosion, life goes on. So the sensor doesn't give you any signal anymore. Also, there are materials like PVDF that are compatible with flexible substrates. They are stable under stress and compatible with the fabrication technique that we wanted to use. There would be other options for other applications. This is how the sensors look like, are designed. So they are basically mechanical sensors, but instead of using photolithography and machining to make these MEMS type devices, we used printing, where we printed the spacers and we laminate a PVDF foil to those spacers. So the pressure sensor and the acoustic sensor are pretty much the same thing. They operate at different frequencies. And the acceleration, we looked at two designs where you have a proof mass that if there is acceleration will basically squeeze your piezoelectric film, or a cantilever where if there is acceleration, the cantilever will have this displacement here, and that displacement will give out a voltage. So if you remember, we use the same material for the memory and for the sensor. In the case of the sensors, this dipole displacement gives out a voltage, which is the output of the sensor. And then when this voltage gets to the memory device, the memory material, it leads to a dipole displacement that can be recorded as charge. So the same material used in both. So how did the sensors look like? We actually delivered lots of sensors to DARPA. Here are the pressure sensors and the acoustic sensors. Here's a commercial sensor signal, and here was the PARC sensor. So you can see that the trend and the curve is exactly the same. This is for a 4 psi blast. The trend is the important thing here because the actual values that you have there will depend on the geometry of this sensor. How well did they work? They were actually quite good. You can see here, this is going from pressures from 10 to 100 psi. So for very low pressures, we had high error. But from 10 to 100, our error in the measurement was about, the accuracy of the sensor was around 2.53%. So if you think about that, one sensor can give you measurements from 10 psi to 100 psi, that's really good. It was a good proof of the feasibility of the technology. Another detail, we always measured these sensors that we made here against commercial sensors. Our sensors cost about 10 cents to make. The commercial sensors are about $1,000. And that's why people are interested in this technology. So we got to the point where we started some integration. We integrated printed amplifiers, you see, in a very crude lab way. That's how life goes. Printed amplifier with a printed accelerometer in this case. The amplifier is basically an inverter. And here we could give a calibration curve for our accelerometers that were really you would measure the output after you went through an organic-based amplifier. So there is plenty of work to do. And I'll give you some examples very quickly. I will stop talking eventually. So here, if we look at the technology today, we are more or less here where mobility of reliable process, where you can repeat for many transistors, is about between 0.1 and 1 centimeter square per volt second. And printed channel lengths vary between 100 micron and 50 micron. This is where we are today, realistically. It's obvious that if you increase mobility, you gain on the frequency, on the operating frequency, which means that you can apply this for other applications, not only for slow electronics. But you can see that there is a much bigger jump in frequency if you actually improve the printing technology. So if you are able to pattern much smaller features or smaller channels, combined with the good and stable mobilities that we have today, you will be getting to play in applications that are more interesting, or there are more applications that you can apply the technology for. So if the electronics gets better, everything gets better. And I'll give you an example of the memory. So the memory that we did was, it worked for our purpose, but it's not the type of memory that you want in your computer. And the memory resolution was really only 2 bits, which means that if you have a 10 psi pressure, your error, it will be plus or minus 2.5 psi. If it's 100 psi, your error will be plus or minus 25 psi. You can see the disadvantage there. If the electronics were better and faster, we could print an ADC, an analog to digital converter. And by being able to print a better electronics, or better building block of electronics, we could increase the resolution of the memory to 4 bits, and you can see how the resolution would have an effect on the accuracy of your measurement. So these things all go together if you're building a system. smaller features. I really like what this group in Korea is doing, because they took like the row-to-row printing everything to heart, and they really do printing everything, but they have limitations. So here, I think this is a 16-bit RFID tag, and you can see how big that is. And that's because of the resolution of the printing. So you have a 16-bit RFID that is as big as the face of that person, and that's really because the printing technique has not gotten to a point where you can shrink the features, like in conventional electronics we have done. So I'll skip the power because I ran out of time, and I will finish here by saying thank you to my wonderful colleagues at PARC. Jörg and Daniel worked a lot on the sensor development. Leah and Tina have done a lot of the work for the memory development and some of the electronics. So did Greg Whiting, who was the chemist in our group, and he taught us about the materials. Steve Reedy designed all the printers that we have. Bob Street is the smartest person I worked with and the best boss that one can have. And Brent and Raj also helped us with the design of the electronics. So thank you for the money sources, and thank you again for giving me the opportunity to talk here.